My name is Justin Murray, and I seem to have been promoted on the slide. I was a systems engineer when I walked in, and now I'm a staff engineer, so feel very pleasant about that. Somebody promoted me without telling me. This is Richard S., who's from Bull. The reason I won't say his full name is that we have a competition. Anybody who can pronounce Richard's second name, please come to us afterwards for a special prize. You have to pronounce it correctly, though. And Richard is going to do the second part of the talk this morning. He's going to actually describe his own customer's actual implementation of Java and WebLogic on vSphere. So I'll call Richard back up in about 25 minutes or so. Just to get a feel for the audience, how many people have already virtualized their Java? Well done, 90% of the audience. How many people have virtualized WebLogic server? Maybe about 20%. People who have virtualized Websphere server? Maybe about 20%. And virtualized JBoss? That's a bigger number, maybe about 30%. And then virtualized Tomcat? Wow, that's the big one. And I have some news about Tomcat during this talk as well, by the way. And then, how many people have virtualized something other than those 4 application servers? Quite a lot of people. So I think everybody in the room is fairly comfortable that Java is a good candidate for virtualization. What we're going to do in this talk is give you some best practices that we've derived from about 4 to 5 years that I've been in VMware now, watching customers virtualize it, occasionally make a mistake doing so, watch partners virtualize Java. We work with a whole bunch of partners, IBM WebSphere and others, to derive the best practices that you should use. And I'm going to give you these best practices, but don't treat them as the law that you have to follow, because in some cases, Richard is going to show you customer examples that actually detract from the best practices that I've actually contradict some of the best practices that I've given. So there are cases when you'll break these best practices that I'm going to show you. I'm going to skim very lightly over why you should virtualize Java, because I think pretty much everybody in the room is convinced of that already. So why do it now? Well, it's a good candidate for virtualization. In fact, it's one of the best candidates for virtualization that I see out there. And I've spoken to about 150 different organizations, customers, partners, etc., who are virtualizing Java just in the past year or so. An awful lot of people are doing it. It's a very popular thing to do. So why do it now? Let me skim lightly over that. We think it's a great candidate for virtualization. Middleware applications have undergone a lot of testing inside VMware, a lot of testing inside HP, IBM, other places at Bull as well. So we believe the performance of Java-based applications comes very close to the performance of the same setup on physical systems. In other words, you should come to within 15% at the very most of your physical system. In some cases, we found that virtualized Java behaves almost equal with the physical system. That's not the case for every application, but in some applications that we've seen, it's pretty much the same behavior on virtual as on physical. And it's important to measure like with like. So measure a 4 virtual CPU system against a 4 physical CPU system. It's important to do that like for like measure. We believe that middleware, in fact, in our case, Tomcat is almost the first application to go into the cloud. So virtualizing Java we see as a first step to taking it into the cloud, whatever your cloud may be. These are the things we think you get as a benefit from virtualizing it. You get isolation, consolidation, rapid provisioning, and some other things as well. I won't dwell on these. These are the things that persuaded you to virtualize your Java. I'll go straight into the technical section here, which is what are the best practices that we recommend to customers when they're virtualizing Java. And there are 2 main ones. The 2 main ones are at the top there. They are take care of memory, because Java is very sensitive to memory, and I'll explain why. And then when it comes to the question of virtual CPUs, the general best practice is rely on as few virtual CPUs as you can get away with. Now, Richard, when he talks about his WebLogic application, is going to show you an example where the best thing for them was an 8 virtual CPU VM. But in general, your starting point should be a 2 virtual CPU VM. Test with that first. And then choose to do the same test with a 4 virtual CPU or even an 8, just to see how much benefit you get from it. But there are an awful lot of Java applications in the world who will do fine with 2 virtual CPUs. And that's pretty much the best practice there. So I'm going to focus on those 2. There are others that you see at the bottom there, which are fully described in that paper, vmware.com/resources/tech-resources/1087. That's kind of our master document for collecting best practices together. And by the way, I'll ask you to hold your questions till the end because we have an awful lot of material, but we'll hang around afterwards and talk to you about and take a question and answer session at the end. But that's our master document. If you have any best practices yourselves, we'd love to get hold of them and put them into the next rev of that document. So I won't describe the bottom 4 at all here because they're best practices no matter what you're virtualizing. If you're virtualizing Oracle databases, if you're virtualizing Exchange, if you're virtualizing DB2, you would do those things anyway. They've got really no relevance. They have got relevance to Java, but they're not special because of Java. The top 2, however, are the things that we pay most attention to. And I'm going to start with memory. And here's an ESXi server. I should be using ESXi now, with 2 virtual machines on it, one of which is running Java, the simplest example in the world. And I'm going to get more complicated here in a second. So I put the Java heap in a different color here, and that's the thing that you specify with -xms and -xmx when you're calling your Java program. And by the way, I'm not going to have any code examples here. We're not talking about coding Java. We're talking about deploying Java in this talk, deploying it at production time. The Java heap is the most sensitive area in the Java world. It's where all objects are born. It's where they spend most of their lifetime. It's where Java does most of its work. So above everything, we've got to make sure that the Java heap is in physical memory even when it's in a virtual machine. And what I mean by that is we've got to stop it being swapped by the guest operating system. We've got to stop it being swapped by ESX. We've got to stop it being ballooned by the traditional balloon driver. And I'm going to introduce a new balloon driver here, which is not the traditional balloon driver, which actually goes into the Java heap itself. And that's going to be at the back end of this best practices session. But above all things, as a starting point, as a starting best practice, do not allow the Java heap to be swapped either by the guest operating system or by the ESX server. And I'll show you how that could happen in memory overcommitment situations. So we're going to delve into that Java heap for about 1 minute here. We're going to take a snapshot of Java, the lifetime of a Java program for about half a minute. And the Java heap is made up of several sections, as you know. I'm sure you've seen this before. This is the standard layout for the Sun JVM. The young area is where all objects are born, and the old area is where they live if they've lived for a long time. And we're going to look at this now, and remember, this is being managed by the JVM, which is being managed by the guest OS, and the guest operating system is being managed by ESX. So there's 3 layers of memory management here. And the way in which Java manages memory is when I create my first object, it goes into the Eden area. And then I create my second object and my third object. And I've simplified I've simplified this. This is more complex. These are thread local allocation buffers and all this. But you can think about it as objects being created in this nursery area. And when you fill up the nursery or the Eden area, it's time for a minor garbage collection. And a minor garbage collection happens once every 1/10 of a second or so. Nothing unusual about this. And by the way, do not be worried that garbage collection might operate differently on VMware than it does on physical systems. It operates exactly the same way with the same parameters. So we get a garbage collection event. This is a scavenge garbage collection. It's a very fast one. It collects the objects which are no longer needed and clears out the space. And some objects are needed beyond that garbage collection. This is very normal. It happens sub-second. It probably happens in 1/100th of a second or so. And then it starts again. We build up new objects, and this is constantly happening. Remember, we're within the first 30 seconds of the lifetime of a Java program here. By the way, the rate at which you're creating new objects is called the object creation or allocation rate, memory allocation rate. And if your memory allocation rate is faster than your garbage collection rate, then sometime in the future you're going to run out of space. So that's an important thing to bear in mind. We get a second garbage collection, quite normal, happens normally. And these are all pages of memory being managed by the JVM here. And here we have 3 survivors. The rate at which you survive is determined by a runtime flag, survivor ratio. You don't have to change any of those runtime flags because you're going virtual, by the way. And so you've got some survivors, and eventually those survivors live for a long series of garbage collections. The default is 32 garbage collections, and they get tenured. They become tenured professors. They're going to be around for a while. They're old objects. They've been used over and over again in the Java program. And that's very normal. You see that happening all the time. And eventually you're allocating more and more objects, and you could, in some cases, fill up your tenured area. Now, this is something that most Java people worry a lot about, because if this entire heap space is 8 gigabytes or 4 gigabytes in size, and you're working fairly hard in Java, there's a certain component of the next full garbage collection that's called a compaction phase, where you actually stop all the user threads. It's called a stop the world. And most JVMs, when they're compacting the used objects, the objects which are going to survive the full garbage collection, they stop the world. And so there's a pause. And many, many Java programmers oversize their Java heap for exactly to avoid this condition. In other words, they add in some rule of thumb space into the heap. They make it bigger than it really needs to be because of this condition. They want to avoid this condition at all costs. That's called a full garbage collection. We have seen situations where this could stop the program for several seconds if you get a large heap here. So nothing different in virtualizing this is exactly the same. And you can see this is a very, very busy area. The Java heap is extremely busy. Things are going on there all the time. So we survive the full garbage collection. We get some space, and you'll notice all the objects are compacted down to the left-hand side. That's the compaction phase. Those are the objects that are still in use. And that's the stop the world phase there, that compaction phase. Nothing different on VMware than if it were operating on physical. Completely the same. Now, the reason I made the point about people building the heap bigger than it should be is that wastes memory, really. If you can survive in this condition here where you're never ever going to fill, then why have that extra space there? And actually, virtualizing has one side benefit, that if you look at the active memory in Virtual Center, you will actually see how much this Java program really needs, as opposed to what your Java programmers are telling you they think it needs. You can see the amount of heap space that is actually need when you look at active memory, at peak load, that is. And that's a good way of measuring exactly how much overhead the programmer has put into the heap space. I admire them for doing so. They've done this for a long period of time, but it's really wasting a bit of memory there. And I'm going to introduce the balloon driver into this heap space now to get that memory back if there's wasted memory there. Not the traditional balloon driver, it's a new one. So now we're going to go down 2 levels, down beneath the guest OS, into the ESXi hypervisor itself, and see what's going on there. Remember, we're on floor 2 here. We're now going to go down to floor 0, which is where the memory is really being managed at the hardware level. So the Java memory that I was just talking about is that top level there, the guest virtual machine memory. The guest operating system doesn't know this is Java. It's saying this is a highly consuming Java process. And beneath that, the guest OS is mapping the Java pages of memory to what it believes is physical memory. That's the middle layer there, guest physical memory. Of course, it's not really physical. The ESX hypervisor is dealing with the physical memory. And guest physical memory is being mapped to machine memory by ESXi, by the memory management unit inside ESXi. Well, in contemporary hardware, Nehalem hardware, AMD Shanghai hardware, anything that is post Intel 5500 Xeons, that mapping at the bottom is being done in the hardware itself. It's called rapid virtualization indexing in the case of AMD, or extended page tables, EPT, in the case of Intel. And my first encouragement to you and my first best practice is get onto the latest hardware for your Java virtualization. It will assist Java to the point of giving you somewhere between 5 and 15% benefits in performance. That mapping that is done there between the guest physical memory and the machine memory should be done by the hardware nowadays. And so when ESXi starts up and sees what type of hardware you have, it will do this automatically. It will delegate the memory management to the hardware and hardware-assisted technology instead of doing this in software. We still have the software method of doing it, but we only use that for much older hardware. So use Nehalem, use post-Nehalem hardware, use Websphere, or use the latest AMD, Shanghai, and later hardware. That's tip number 1 for getting the best out of your Java. Tip number 2 here is you see that page B in green is being shared across those 2 VMs. ESXi has got an algorithm inside it that at once a minute scans all the guest physical memory pages and says, this page is a page of zeros, this other page is a page of zeros, I'm only going to store 1 physical page for that. That's what gives you the ability to pack more virtual machines into the physical memory than will actually fit. For example, I've seen customers pack 14 gigabytes worth of VMs into a 10 gigabyte or 12 gigabyte memory space. That's called memory over commitment. And I want you to avoid doing that with your Java, with your production Java systems. And when I say Java, I mean production Java nowadays, as opposed to developer time Java or testing time Java. Do memory over commitment with those if you like. But with production or important SLA-driven Java, do not memory overcommit, with one exception. And I'll give you the exception in a few seconds. In general, make the sum total of the active memory of your virtual machines fit into your physical memory. In other words, if you've got 14 gigabytes of active memory being used by your virtual machines, put it into a 16 gigabyte box. Leave a little extra space for ESXi to do its work. So even though with VMware you have the capability, because of this transparent page sharing, you have the capability of packing more virtual machines into the physical space than will actually fit, avoid doing that for Java with one exception. And that one exception is Tomcat based. And I'm going to talk to you about that in a second. I'm going to give you now a second best practice, which is these memory pages at the guest physical memory area could be 4K in size, or they could be 2 megabytes in size. And it is up to you, the developer or the deployer, to choose that memory page size. And my recommendation as a best practice is use large memory pages for Java. In other words, tell the JVM, I want to use 2 megabyte pages, and tell the guest physical memory, guest operating system, I want to use large pages. You do that by means of a JVM switch -XX use large pages. Or if you're using the IBM JVM, -XLP. It tells the JVM to use large pages. And you do it on Linux by incorporating huge pages. There's a white paper on this, Linux best practices using large pages. So if you use large pages, this memory page sharing at the bottom is effectively no longer operating. Because these are 4 megabyte or 2 megabyte pages, it's far more difficult for the scanning algorithm to find 2 guest memory pages that look exactly the same. And so it says, let's not bother sharing. So the question of page sharing is really switched off with large pages. I'm going to summarize these points in a minute here. So this is ESX trying to conserve memory at all costs, because memory is the premium in Java especially, and in other systems as well. One action that the ESXi hypervisor will take if it sees memory becoming pressurized, in other words, if you're piling on the virtual machines into your physical memory and there's a shortage, it's less than 25% free, then ESXi will pick a victim among your virtual machines. It's a virtual machine which is not really actively using its memory very much. And it will invoke the balloon driver, the standard balloon driver, which you should have switched on in almost all cases. Have it switched on, but not have it active. Now, what the balloon driver will do is say, guest operating system, I'm an important process, give me some pages of memory, give me 100 megabytes of pages of memory, and the guest operating system may have that much free on its free list, and if it does, it gives it to the balloon driver hands it to ESXi, and now you have some relief from the memory pressure that was there previously. The balloon driver, however, could actually balloon some of the Java heap pages. It could in extreme circumstances. And if it balloons some of the Java heap pages, then you've stolen physical memory away from Java, and that's not a good thing. So I don't want to ever see the balloon driver being active in a virtual machine in which we have critical Java running. In other words, a production Java system. This is the standard balloon driver now that comes with VMware tools. Once the pressure goes away, the balloon driver gets deflated and the memory goes back again to the virtual machine. Although the balloon driver should be switched on, I don't want to see it stealing pages away from virtual machines at any time. And you see that using mem control size in vCenter. There's a counter for every VM that shows you what the balloon driver is doing. It should be at 0. Okay? Finally, if ESX says, I've tried the balloon driver, I'm still under memory pressure, memory is getting very low, I'm less than 10% of my memory is free, the next virtual machine that starts up is going to kill me, it starts swapping. And for every virtual machine, just like in traditional operating systems, for every virtual machine, ESX has a swap file. And that swap file allows it to swap that virtual machine out to its disk. Now, this is not guest operating system swapping. This is swapping at the ESX hypervisor level. I want you to avoid both for Java. Of course we want to avoid it because it's to do with memory, and we don't want memory going anywhere for our Java program. So we don't want this to take effect either. And this would only take effect if you memory overcommitted the box. So if you stay out of memory overcommitment, then you're going to be fine. By the way, most cell phones have Java on them as well. We obviously have a user here. Oh. I heard there were 6 billion devices running Java at the moment. So the golden rules then are size your virtual machine for adequate space. When you have a choice as the person who's setting up VMware. Size your virtual machine to leave adequate space for the JVM. In a simple case, you have one JVM inside your virtual machine, but you could have 2 or 4 or more if you want to. You can have as many as you like. Start off with one and do your testing with one. Then add another one and see what it looks like when you're testing. Build them up quite slowly. But size the virtual machine to have adequate space for the Java heap space. That's extremely important. For any other memory demands of Java, that's the stack space, and we have a formula in the best practices to allow you to calculate that. And for any other memory demands that might be there, like another JVM or a monitoring process, make sure you leave enough space. I had one example, for example, where a customer said to me, I have an 8 gigabyte heap. That didn't scare me. I have an 8 gigabyte heap, and the size of the virtual machine is 4 gigabytes. Clearly not going to fit, right? It should be the other way around. So in my testing of application servers, my heap is about 1.6 gigabytes. The virtual machine is configured to 2.2 gigabytes. Leave plenty of space there for the guest operating system or for anything else that's going on. At least half a gigabyte for Linux is my recommendation. So essentially what we're doing here is preventing the guest operating system from swapping. In other words, the guest operating system is trying to start Java. It's trying to start any other process. It doesn't have enough room because the virtual machine is too confined. It starts swapping. That's not going to help your JVM process. And then if you have a production Java system, or if you're troubleshooting the performance of a Java system, whether it's production or not, the first thing that we do is we set a memory reservation. And the memory reservation is a cast iron guarantee that that virtual machine, no matter where it moves, or no matter where it gets restarted by HA, will never ever sacrifice its physical memory to anybody. Not to the balloon driver, not to swapping. That virtual machine is cast iron guarantee it's getting its memory reservation. Now, if you want to be conservative about this and a little bit wasteful of memory, you can do the full virtual machine size. You can set the reservation to the 2.2 gigabytes that I said. If you want to be a little more accurate about your reservation, you can do some testing under load, see what the active memory is that I mentioned before in vCenter, and set your reservation to that size. Set the reservation for production Java that could get into a memory overcommit situation. We have one example where a customer vMotioned a virtual machine containing Java from one box to another. No reservations set. The box to which it was moved was short of memory. The JVM began to lose performance because Memory was overcommitted on the target box, not on the origin box. If you set a reservation around that virtual machine, it will only be started on the target box if there's enough memory to satisfy the reservation. So the reservation is cast iron. Nothing can interfere with it. Now, it has some implications. In other words, if you set the reservation too big, you're possibly wasting space, and you can only restart that virtual machine on a machine that has enough to fulfill the reservation. So it has some downside. You don't have to do it for every Java program. You do it for your production SLA-driven Java programs. Don't do it for developers unless they complain too much. And use large memory pages. That's a flag to the JVM and a flag to the operating system, which is documented in the white paper. And use VMware Distributed Resource Scheduler. We've used that a lot with our Java programs. It load balances across very well and is a good thing to use. That's memory, and that's how to set a memory reservation. And you're going to say to me, by the way, I have 100 virtual machines running Java. I'm not going to do this for every one. You can do this using the command line and scripting if you want to set a memory reservation. So there is one exception to memory overcommitment, and that's called elastic memory for Java, and that is a new balloon driver that is different to the standard VMware balloon driver. This balloon driver goes into the Java heap itself. And this is a feature that we ship with our flavor of Tomcat called TC Server. And what it does is causes garbage collection to happen in the JVM in which it's active, steals those memory pages that are freed up by the garbage collection, and passes them back to the hypervisor for use by other JVMs around the place. So effectively, you can think of the top JVM there as a spare reservoir of memory. It's not very active. It sits there and holds onto the memory. And when the other JVMs need it, the memory can be stolen away by this elastic memory for Java program that was written by VMware engineers and fits into the Java heap itself. It's effectively an agent that you can attach to your Java program. We ship this with Tomcat or TC Server today, which you can download for free. It only works with vSphere 5. We did some modifications to allow it to work for vSphere 5. And really, it's something that operates at the JVM level. So I'm giving you a strong hint. A lot of you are WebLogic or Websphere users. It's possible that this could work with your system too, even though we support it with Tomcat. So it's called Elastic Memory for Java. It's a new type of balloon driver, a Java-specific balloon driver, and it fits into the heap. It's nothing to do with the standard balloon driver. In fact, you would switch the standard balloon driver off if you were going to use this. That's one case where we've proven to ourselves you can do memory overcommitment with Java. So as I mentioned at the beginning, these are rules, but there are exceptions to them. And this is the one exception to memory overcommitment. In some testing, we've done 20 to 30% memory overcommitment with this box. So better consolidation with this. So now number two, best practice number two. Best practice number one is all about memory. Use the latest hardware, use a memory reservation, use large pages, and don't get into swapping. Guest OS. Number two is, how many virtual CPUs is ideal for my Java? How many people here are using 2 virtual CPUs for their Java systems? About 20%. How many people are using 4 virtual CPUs? Smaller number, maybe 15%. How many people are using 8 virtual CPUs for their Java system? Very small number. How many people are using 16 for their Java? There's one person on vSphere 5. Okay. So more is not always better with virtual CPUs, and I'll explain why. Here's physical CPUs on the right-hand side. This is a quad-core 2-socket box, fairly old box. And this is a JVM on the left-hand side running inside a virtual machine with 1, 2, 3, or 4 virtual CPUs in it. Could be up to 32, of course, nowadays. Well, the key question is, how many Java threads are really active at any one time? When you do a kill -3 on a Java process, it will spill out on the standard output exactly what's going on in every thread. But it's not necessarily the case that the program was written well enough to be highly concurrent. In other words, although I've shown 4 threads in red there which are running, and 2 threads in green which are ready to run, and 1 thread which is waiting. This is actually quite the opposite of many Java programs that we've looked at. We've done kill -3 on them. That, by the way, is not a destructive call. And you will see something in the order of 200 threads inside many Java programs, most of which are sleeping most of the time. In fact, it's rare to have more than half a dozen to 10 threads that are either ready to run or running at this point in time. So those red threads are being mapped onto the virtual CPUs by the guest operating system. That's what's doing that mapping. It's saying, I need a CPU. It happens to be a virtual CPU, although the guest operating system doesn't know that. It thinks it's a real CPU. And it maps those threads onto those CPUs by the guest operating system. The mapping of virtual CPUs, which you can think of as software representations of a physical CPU, the mapping of virtual CPUs onto physical is done by ESXi. And I should go back and say, a Java thread only executes on 1 virtual CPU at any one time, and the virtual CPU is scheduled on only 1 physical CPU at any one time. It cannot be spread across 2 virtual CPUs. So the question then becomes, why doesn't the slide move forward? The question then becomes, what's the right number for me? What's the right number? And I can tell you the answer, but only in one small corner case. In the vast majority of cases, you will have to do some testing to find the right number of virtual CPUs. And the right number of virtual CPUs, with one exception, just as the memory balloon driver is an exception, the right number of virtual CPUs is the smallest number you can find that will give you SLAs that are correct for your application. So determine the best number of virtual CPUs for your VM hosting your Java application by doing a test with 2 virtual CPUs, 4 virtual CPUs, or maybe 5 virtual CPUs. But I suggest that for something like 60 to 70% of the Java programs out there, 2 virtual CPUs is a good starting place, and 4 virtual CPUs is the second test that you should do. Now, Richard, my co-speaker, is going to show you an example where he chose 8 virtual CPUs, not for performance reasons, for other reasons. And you're going to see that in a few minutes. But using the lowest number of virtual CPUs effectively gives the ESXi hypervisor less work to do. In other words, it's having to service interrupts for every virtual CPU. It's having to service timekeeping clock interrupts for every virtual CPU. The less it does of that, the better. That is, the more time goes to your actual VM. The one case in which I can tell you categorically the number of virtual CPUs that are ideal for your JVM are if you're using this multi-threaded GC algorithm, which I've only found 1 or 2 cases among the many customers that we've talked to, is actually in use. And that's -x GC threads 4. So that is the programmer telling the JVM, I know better than you. Now, there's only been 17 years of R&D work, thousands of people working on the JVM, but this particular programmer knows better. And this particular programmer says, I need 4 GC threads whenever GC starts. And, you know, I've met some folks who've spent years studying this GC algorithm and years experimenting with it, and they found that this helps them. I'm not recommending it for all of you, but for particular cases, this has helped. And in that particular case, you're going to need 4 virtual CPUs when the GC starts up because 4 threads are going to be running concurrently. So I can tell you, you need 4 virtual CPUs at least there. In general, though, for most applications, start with 2 virtual CPUs, and you could think of it as 1 virtual vCPU for my application and 1 for my GC, or 4 virtual CPUs. In many cases, will give you between 10% and 50% performance increase. So that's the best practices in a nutshell. You should also monitor these things, which are separate from the main topics. You should monitor your disk I/O using vCenter to make sure that your average latencies, in particular the K average, D average, and G average numbers. K average is kernel average latency, D average is disk average latency, and G average is guest average latency. And those are the latencies that are stopping you from getting better throughput on your disk. That's not really a frequent thing with Java, although disk I/O is often a bottleneck with other systems. Java, it turns out, in many, many cases, is not disk I/O bound, because all it's doing with the disk is writing log files or writing configuration data out to the disk. It's not doing a lot of disk I/O. Java does tend to be network I/O intensive, so watch carefully your packet send and packet receive rates and make sure you're not overburdening that network card or network switch. In other words, that the amount of network I/O you're doing is within the tolerance of that network card that you're using. Be careful about timekeeping. Set your ESX level timekeeping to an NTP source. And make sure inside your guest OS that you're using the same NTP source for Linux or W32 time for Windows. How many people here are virtualizing Java on Linux? Well over 50%. And how many people are virtualizing Java on Windows? Smaller number, but maybe 40%. So there are different timekeeping rules that apply for Windows guest operating systems to Linux. Linux is NTP source for time. Windows is W32 time. There's a whole white paper that describes this, both in the Java best practices and in the Linux timekeeping and VMware timekeeping best practices. For monitoring and management, if you're starting out and virtualizing your Java systems, one Java process at a time. Test one Java process inside the virtual machine, make sure that works, and then build up the number of Java processes over time. And use the most recent versions of the hardware, Nehalem and the equivalent AMD, Shanghai, and use the latest version of vSphere. We'll show you an example now with Richard of using WebLogic on vSphere and performance of that. So one last summary before I bring Richard up, which is that best practices paper is vmware.com/resources/tech-resources/1087. I was part of the team that helped to write that. I'd like your feedback on it. Imad Benjamin, who's speaking at 11 o'clock here, bullet point number 3 there. He's the author of the current version of that paper, and he's also coming out with a new book on enterprise Java applications architecture on VMware. I have some forms here that'll get you a 20% discount on that. It's not published yet, but it's coming soon. And then he's speaking at 11 o'clock in the Venetian Ballroom 1 on very similar subjects for Java on VMware. He's actually got somebody from the Websphere side who's implemented Websphere. Richard, my co-speaker, is going to talk about WebLogic next. The summary then is that we think Java middleware applications should be virtualized. It's a natural platform for them. As you can see, we're doing innovations inside the hypervisor and innovations at the balloon driver level to make the two work together and coordinate together better. We've done extensive testing on Java of all kinds, including testing of that new elastic memory for Java that's inside the Java heap. And in some cases, that will give you better memory management than the situation before. We think in some of our tests and in many of our tests which are validated by HP and IBM and others that the performance of our Java-based systems, if properly tuned using these best practices, can come close to and even equal the performance of native. So you shouldn't be afraid of performance there. And we think this virtualizing Java is the first step to taking Java into the cloud. So now I'm going to ask Richard to come up, Richard S. Anybody can pronounce Richard's name yet? And he's going to talk about what Bull Systems did to virtualize WebLogic.
Morning. Okay, so basically what we try to do is that we deployed WebLogic on vSphere 5. So vSphere 5 just got announced, so I think we were a little bit ahead of the majority of you guys who did already vSphere 5 deployment for Java 1. Oh, okay. So we were a little bit ahead. So as you can hear, I'm not a native American. I'm from Europe. So maybe that's why we're a little bit ahead. No, I'm kidding. So what I try to help you with is showing you that you can deploy large WebLogic production environments on vSphere 5. We can have, because this customer is coming from a Unix world, So we can have the best of both worlds in terms of Unix and Intel. So limit the number of virtual machines while reducing significantly the TCO versus Unix environments. Justin just mentioned that having the best performance is being obtained with 2 vCPU Java deployment. So I'm going to show you that in this environment we use a different kind of architecture specifically to reduce the TCO, because deploying a large number of virtual machines means a lot of maintenance and therefore an extra burden for you guys. A quality of service which is close to Unix environments thanks to new Rust features and, of course, application high availability. So this customer is a 50,000 user French public body. And as you know, in Europe, we have a key problem, which is public sector spendings. We spend too much and there's not enough income. I think you know the concept a little bit as well. So, of course, what the key pain was that this public body is in charge of benefit payments towards unemployed people within France. And the government needs to do more with less, so more with less money spending. So today, or in 2010, this Websphere, WebLogic environment, was running on 6 Unix systems, over 200 different partitions, using a total of 5.5 terabyte of RAM. Okay, so it's a pretty big infrastructure. And the objective was to reduce TCO and get to a first step to migrate away from proprietary infrastructures, because they still have a large number of Unix and mainframe systems. So what we have done is, I'm skipping this because it's maybe a little bit too much marketing. We have deployed 4 systems, these guys. Okay, so it's one single server able to scale up to 16 sockets with 128 cores, Nehalem cores, and until now limited to 2 terabyte of RAM. And thanks to vSphere 5, we will able to go over that. And we have a performance which is higher than any Solaris system available in the market. So this system is more scalable than any other Intel server in the market. So we did a day trader benchmark to help our customers to size the appropriate number of virtual machines to deploy and to get to an architecture where we needed less virtual machines than in the initial Unix environment. And to provide and to prove that robust scalability can be obtained with virtual machine and is in line with Unix architectures. In addition, we needed to demonstrate an efficient alternative to mainstream scale-out architectures. I suppose you're all using a scale-out architecture. Who is running Java virtual machines on Blade servers? Okay. Who on rack servers? On 2 sockets, 4 sockets? 2, okay. So here, basically what I'm trying to show is that we have developed an alternative with more scalable systems and therefore using less number of servers and provide a robust infrastructure. So this is the test configuration. So 16-socket system with 1 terabyte of RAM, running ESXi and Red Hat WebLogic 9. We have also virtualized the load runner on a smaller Boolean server with only 4 sockets. and we run the database server on a separate Unix system, all connected to the same EMC box. And what we have shown here is that when using 6 gig per vCPU, so that means 12 gig for 2 vCPU virtual machine, we get with a single relative performance WebLogic instance a relative performance of about 100. Well, if we increase this virtual machine to a 16 vCPU infrastructure running on a 96 gig RAM, we increase the performance to almost 400. So this is where you show that why Justin recommends to use smaller virtual machines, because then you have the best price-performance ratio. Now, if you add an extra instance into the same virtual machine, you get to a much better performance because you get over 700. For our customer, this was significantly enough to deploy this kind of infrastructure. So he didn't care about having the best performance possible. He cared specifically on reducing significantly the number of virtual machines to run. We did a little comparison between our Boolean servers with Blade servers using Intel Xeon 5400 processors. And here you see a little difference. So to obtain the same performance with the Blade servers, we needed 88 Blade servers. Well, with Boolean, we could use only 4. Okay? And this, of course, less servers, less maintenance, less networking, less connectivity, less administration. This is basically what I'm saying here. 88 servers versus 4 servers. 217 virtual machines versus 55 virtual machines. So a lot more network connection, more power consumption, and of course, more floor space used. Now again, using larger virtual machines doesn't provide you the best performance, but reduces significantly the administration and management. With the Boolean servers, we sustain easily those large virtual machines because we can still use Justin's best practices by not overcommitting memory, nor using more vCPUs than physical CPUs inside the box. And therefore obtaining very easily the gold level SLA. So with larger virtual machines, you keep it simple. You keep a simple infrastructure and therefore less maintenance, less patching, and less servers to maintain. We still have a significant increase in very good quality of servers, so we expect that this is a very good alternative to traditional scale-out architectures. So as you can see, the Boolean server is quite performant. You can see it is 144% faster than any IBM system in the market, and 47% faster than any HP system in the market. This is not us saying that. This is a benchmark done on spec-int rate, which is a benchmark showing the performance of different servers. And we are the only server able to overpass the 3000 range. Now, you say, why should I care? Spec-int rate gives a very close indication to the performance you can obtain with spec virtualization. It's another benchmark from the spec organization. And there is a direct link between spec-int rate and spec-virt. So during the VMware EMEA session, we will announce the spec-virt of this machine. And we expect to overpass the limit VMware vSphere 5 is able to maintain. So, as a conclusion, business-critical applications can be deployed on vSphere 5, and you can use alternative architectures based on larger server nodes. Scalable servers enable this customer to concentrate and consolidate its applications by reducing significantly the number of virtual machines required, going from over 200 virtual machines to 55 virtual machines. And thanks to the scalability of VMware vSphere 5, only this is possible, because before we were limited to 8 vCPUs. And WebLogic Server scales very well on VMware vSphere 5. We didn't do yet the test between native and virtual infrastructures, but this is a test we are planning to do. And the white paper we will get out on this will be available in October on our website. So don't hesitate to migrate to vSphere 5 and deploy large virtual machines in order to reduce significantly your administration costs.
Thank you, Richard. Thanks very much.
Thank you.
I'd just like to introduce one more person to you. This is Ben Currie from our senior engineering team. This is the gentleman who architected and designed and implemented the elastic memory for Java driver that goes inside the Java heap that I mentioned to you. We're shipping with TC Server and vSphere 5. So it ships out with the vFabric 5 and TC Server 5. Ben's offered to stick around and answer your questions on that. This is probably the most exciting technology we've done in Java for a while. And we'll be around here for a little while to discuss these things with you. But it's an opportunity for you to fire a question at us now, please. And any questions, I'm going to delegate to Richard anyway to give the answer. Any questions?
Early on, you were talking about how ESXi uses a page sharing algorithm.
Right.
Is there any way to disable that?
Yes. In fact, when I was recommending that you use large pages for Java, you effectively have disabled it once you've done that. So let me try and get back to that for you. So you can do this in two ways. You can switch on large pages for memory, which is recommended for Java, or you can do it at the VMX file level as well. In general, with your systems, you don't need to switch off this. It's not a performance overhead. In fact, page sharing is a good thing, but if you choose to, you can switch it off. Thank you. Other questions? The question is, will CPU affinity rules help or hurt Java? My vote is that they hurt the portability of your virtual machine across different environments. So we recommend against CPU affinity for virtual machines in general that run Java. There will be special cases, as I've shown you twice this morning. There's always exceptions. But in general, we don't encourage any customer to use CPU affinity rules. So you may have been thinking about the question of what's the mapping of virtual CPUs to physical. If you're being conservative about it, keep the number of virtual CPUs equal to the number of physical CPUs across your box. But if all of your virtual CPUs are operating at 50% or less, there's no reason why you couldn't overcommit virtual CPUs as well. And effectively, a virtual machine is doing some lockdown of its virtual CPUs to physical anyway, by default, without doing CPU pinning. Fair answer? Okay. I'll come back.
Sun JVM.
My reading of the website is the best of JRocket is being merged slowly into the Sun JVM since the acquisition, and the Sun JVM will be the JVM going forward. But they'll take some better ideas from JRocket. That's just my personal reading of the website.
So now with Memory reservations. Now, if you set the memory reservations on a resource pool and have all of your hosts in that resource pool without overcommit, do you get the equivalent experience of setting them on the individual hosts? Or what would be the recommendation there?
Okay, so the question was about memory reservations and resource pools.
Yes.
So a resource pool is a good idea, and we like that idea. However, you can overcommit a memory situation with a resource pool just as you can overcommit an ESX server.
Right,
so
but
it's not the same cast iron guarantee.
But if you're not going to if you manage it appropriately and don't overcommit your resource pool, is there any disadvantage to doing that opposed to setting them on the individual hosts?
That's perfect.
Okay.
If you deliberately set out with a policy never to overcommit your resource pools, which you have to enforce from a management perspective, then that's even better again than setting a reservation on an individual virtual machine.
Okay.
To my experience, it's more interesting to invest a little bit more in memory than do any memory overcommitment. Because honestly, the extra $100 you spend on more memory, you gain back very quickly by avoiding a lot of maintenance and support issues. Okay.
I'm going to let the architect answer that.
So the answer to that currently is no. There is no good technical reason for now why that's the case, other than that we haven't tested it. The situation with the Inf.j is that I literally came back from vacation a week ago, and before I went on vacation, I finished the dev work. So we've literally just cut it. So it's the very first release. It's all brand new. And really, in putting it out in TC server in vFabric, it's a way of ultimately keeping it to a particular application server, keeping it to particular workloads, keeping it to particular kinds of garbage collection. And that's just helpful, at least in this initial release, in terms of putting boundaries around our testing, ultimately. It's interesting, the Websphere question, because Websphere typically runs on IBM's JVM, and for us to support that would be quite a bit more work. That's not to say we wouldn't do it, but it is something that would be a bit more work for us. So.
Thanks, Ben. So the question was, is Websphere supporting the EM4J technology?
Yeah.
No problem. Okay, that's a great question. I've asked that question myself in the past. So the question is, does the scheduler for ESXi wait if four physical CPUs are not available and the virtual machine has 4 vCPUs ready to run? Does the scheduler wait until 4 physical CPUs are available? And the answer is no. We have the notion of loose co-scheduling now. You can look up that term on our VMware.com website. On the tech resources side, there's the loose co-scheduling means ESX does not have to wait for 4 physical CPUs to be available, or for available CPUs before it can make progress with a 4 virtual CPU VM. So the penalty that used to be there in pre-ESX 3.0, we fixed this at ESX 3.0, which was rigid co-scheduling, is no longer there. Hasn't been there for the last 4 versions of ESXi. So don't worry about that. That's called co-scheduling, and the progress that one CPU makes versus another is called skew, and we keep track of that. So don't worry about that. 1 second, please, and we'll come.
I just had a deployment of 8 guests for P8 Content Central using Websphere. And they wanted to increase their CPUs from 1 to 2, and adding more CPUs, the CPU utilization went up. I'm not sure if that's just a function of Websphere or if there was a problem that I could have done differently. As I went from 2 to 4, I even saw more CPU activity than I did with just 2. So I'm seeing something in reverse just on this product, because the Tomcat and the other JBoss, they didn't show any of that, but the Websphere environment did. But I don't control the configuration of that environment, so
Yeah, I wouldn't have expected CPU to go up as you add more virtual CPUs to a VM. I'd have expected it to go down as you were expecting. There may be something going on differently there. There may be extra garbage collection going on, which is really above the virtual machine layer. Check into that first. Make sure that they've got exactly the same conditions applying, that there is no starvation of memory, first of all. That's the check. That's the sanity check number one. Make sure that exactly the same memory conditions apply and that the same load test is being executed as well.
So it sounds like heap size could have been the issue.
As you add more virtual CPUs, you give more opportunity to do more to the machine. So you need to check into that for sure. Yeah.
Appreciate it. Thank you.
But that's an unusual situation. Yes.
Thanks.
Rightly suspected. Other questions, please.
Maybe we...
The question is, what's the position on 3, 5, 7 virtual CPUs? Of course, you can do 1 virtual CPU, 2 virtual CPUs, 3, 4, 5, 6, 7. No preference there. It turns out that the majority of the testing that we've done has been even numbered. I think that I can't really explain why that is, but we tested 2 virtual CPUs and 4 and 6 and 8, and it turns out that for the particular applications like day trader that Richard mentioned, 2 to 4 is the sweet spot. We didn't spend much time with 3. So it's a good question, and we should do more research in that area. Between cores and threads? Okay. So the question is, does ESX make a distinction between cores and hyperthreaded? ESX recognizes that you're hyperthreaded if you are, and will make use of the hyperthreading. But effectively, when we talk about vCPUs and cores here, we mean physical cores. So whenever performance comes into the question, we always just talk about physical cores and ignore hyperthreading. Keep hyperthreading switched on. It's a good thing. But don't take a hyperthreaded core to be twice a non-hyperthreaded core. Absolutely not.
We measured about between 8 and 12% increase of performance when adding hyperthreading. Okay? Sometimes a little bit more than 12, but never more than 15%. So it's really not twice the performance.
We have to move on. Time for the next session.
Okay. Thank you very much.
Thank you.
We'll be around outside.